Thank you very much, and thank you very much for the invitation. So today I'm going to talk about the work with my student Jun Geng. It's about quickest detection. Okay. So here's the outline of this talk. But first, I'm going to introduce what's the meaning of quickest detection, and I will also try to give some applications about this technique. Then I'm going to the technical details, and then I'm going to offer some conclusions. So what is quickest detection? So in the quickest detection, you observe a signal sequentially, and at certain time, the PDF changes. Okay? So in this particular sequence, before time t, the observation is RID according to F0, and after this particular time, the observation is RID according to F1. And our goal is to identify this change as soon as possible. So in this particular case, we are going to use this capital T as a stopping time, in which you are going to say that it's enough. There's already a change. Okay. Then the difference between the time this change happens and the time you raise alarm is the detection delay. Okay. So detection delay is not starting from 0. It's starting from the time the change happens and the time you raise alarm. On the other hand, if you raise alarm before the change happens, then it's a false alarm. Okay? So our goal is to minimize this detection delay, subject to some certain kind of false alarm. I don't want to raise a false alarm too often. Okay? So I want to minimize this. At the same time, I also want to minimize the false alarm rate. So let me give you some applications for this technique. It has been used in a lot of different areas. So the first one is this kind of network attack detection. So you can think of this x1, x2, x1 as the observations you observe from the network. Something as the package rate or what kind of a package type. Right, so it's noisy data. Even if the network is there's no attack on the network, you observe some noisy data. Now, if some bad guy comes and attack your network, then some of the observations, the PDF, the statistic behavior will change. Okay. Now, if you can detect this kind of change as soon as possible, then you know that you can detect this attack very soon. The other application will be this chemical attack detection. You put a lot of sensors around the city, then you take observations. Then if someday some guy comes and release the gas, right? Then the PDF of observation, the sensors will change. And then by detecting this, you will be able to detect this kind of attack very quickly. The other application will be finance. So you don't want to see this, right? But if this happens, you want to detect this as soon as possible. Or this kind of structural monitor. You put the sensors in the bridge. If something breaks down, then the behavior of the observation will change. Then by detecting this change, you will be able to infer that something is wrong. Okay. So it has been used in a lot of different areas. And so let me give you some background about this change point detection. There are two main types of problems. One is Bayes and the other one is non-Bayes. Okay. So the main difference between Bayes and non-Bayes is relies on assumptions about this change time. Okay. So in the Bayes setup, we assume that this change time t is a random variable with certain known PDF. Okay. So for example, we can assume that this change time t is has this particular the PMF of this change time t is according to this PMF. The probability that this t equal to 0 will be pi naught, and the probability of t equal to k is given by this equation. Okay. So in this case, the performance metrics, there are two performance metrics. The first one is the average detection delay, right? So the time you raise alarm minus the time the change happens. Okay. So this the average false alarm. And the second performance metric is this false alarm probability, which is the probability that t is less than or equal to t. So notice that when you compute these two quantities, there are two sources of randomness. The first source is this time, the change time is random. The other one is that the observation is also random. Okay. So when we compute these two quantities, there are two layers of average over there. So again, the goal is to minimize this the average detection delay, subject to the probability that the false alarm is less or equal to alpha. So for this kind of Bayes problem, it's kind of easy. This problem has been solved. So the optimal solution is very simple. So what we are going to do is that after taking each sample, you can go back and compute what is the posterior probability such that a change has happened. Okay. So using Bayes law, and all this kind of probability model, you will be able to compute this posterior probability. Then what we are going to do is that we are going to raise alarm as soon as this posterior probability is larger than a certain threshold. Okay. Then of course the value of this threshold depends on the value of this false alarm rate. Okay. So if you want to make this false alarm small, then this threshold will be big. On the other hand, if this false alarm is big, then which means that you can make a lot of mistakes. Then this threshold will be very low. So this Bayes change point detection problem has been well understood.
So that formulation is the Cheriev formulation.
Yes. Yeah. Okay. So yes, this Cheriev formulation. And now for the non-Bayes change point detection. So the difference is that the change time t is fixed but unknown. Okay. So t is fixed but unknown. This problem is much more challenging than Bayes one. Even the problem formulation is kind of fuzzy. Okay. So there are two main types of problem formulations. The first one is given by Lauder. So let me explain this. So I'm going to use Fk to denote all the observations you have before time k. Okay. So Fk simply means the sigma field generated by x1 until xk minus 1. So now the detection delay really depends on the observations you had before the change time, right? Before the change time. And this is a random variable. So this is a random variable depending on the observations you had before the change time. Now what we are going to do is that we are going to take the essential soup. Okay, because this is a random variable, then we are going to take the essential soup. Then we are also going to consider the worst case over time t. Okay. So in this case, we have two worst case scenarios. The first one is the worst case over observations that happens before the change time. The second layer of worst case is the worst case over change time itself. Okay.
What's an essential soup?
Essential soup is similar to soup, but since it's random variable, then essential soup is simply a quantity such that the probability of that random variable less than this value is equal to 1. It's a minimal upper bound such that the random variable you are trying to consider. So this is a random variable, right? Depending on observation. Essential soup is the minimal upper bound such that the probability of this random variable larger than that bound is 0. Similar to soup, but it's work for random variables. Okay, so in this case, in a London's problem formulation, which we are trying to minimize this worst case scenario, worst case detection delay, and the false alarm constraint is measured by the average run length to false alarm. Basically, essentially, what this means is that, so if I put the average and this infinity here, simply means that there's never a change. Okay? Even if there's no change, but your scheme is going to raise alarm anyway. Now what we are going to do, what we are trying to bound is that if there's no change, then your scheme should not raise your alarm too often. Okay? So this measure the average time between the false alarm. If this is bigger, which means that you are not going to raise false alarm quite often. So again. This is what we call Lauden's problem formulation. We try to minimize the worst case detection delay subject to this average run length to false alarm constraint. So the optimal solution for this problem formulation is given by Cusa. Actually, this scheme was proposed in 1954, but only after 30 years it was proved that this is optimal.
If you go back, what is the expectation over
Where?
there?
This one?
E index T.
EXT simply means that expectation, we assume the change happened at time t, right?
So conditional T.
Conditional on the event that the change happened at t.
And then capital T is random.
Capital T is your stopping time, is your scheme you design.
So you want to find T that minimizes that?
Yeah, you want to find this capital T. You want to decide when to stop to minimize this direction.
But what I'm just like, if you sort of think of capital T minus T plus 1 as a random variable.
Yes, it's a random variable. Yes.
So T is known, little t is known.
No, I mean it's fixed but unknown.
Right, fixed. Yeah, but I mean it's fixed. Right?
It's fixed.
Condition on that it's value T, right?
Yes.
Then the random is only capital T.
Capital T. Yes.
Okay.
I mean, so the reason why capital T is random is because you observe this random sequence, right? Although your strategy is fixed,
Right.
but the time when you are going to stop, it really depends on the observation you take.
Right.
Okay. So it's, this T is also a random variable. So the optimal solution for this problem is something called Q-sum. So let me explain what this means. So let's first take a look at, suppose the change happens at time I, right? Suppose the change happens at time I. Then the likelihood of observing xik is very simple, right? So on the top is before time I, all the samples come from f0. After time I, all the samples come at f1, right? On the bottom, simply assume that the change does not happen. So all the samples come from f0, right? So this is likelihood of change happen at time I if you after observing all the data from time k. So what we are going to do is that, of course, we are going to take the maximum of them, maximum over I, maximum over I. So sk is maximum of this log likelihood over I, and we are going to raise alarm as soon as this quantity, this maximum likelihood, as soon as this maximum likelihood is larger than the threshold. And this is something called Q-sum, and it has been shown to be optimal. And we can intuitively explain why this is true. So let's take a look at the likelihood. Okay? The likelihood before the change. Before the change, if we before the change, then we know that all the samples come from f0, and if you take average, then it's divergence between f0 minus of divergence between f0 and f1 is less than 0. But after the change, the samples they are coming from f1, and if we take average, then it's df1 f0 is larger than 0. So what we see here is that before the change, the average this guy is going down. After the change, this guy is going up. So this is if we plot the sum of these random variables, we can see that initially it goes down, and after some y, if there's a change, it's going up. So what we can do is that at any time, take a look back, okay, to see whether there's a consistent change upwards. Okay. So if you see that it keeps increasing, then evidence is very strong that a change has happened. Okay. On the other hand, suppose you are at this point, if you look back and see that it's always going down, which means that there's no change at all. So the idea of this Q-sum is very simple. At each time, you just go back and take a look at whether there is a consistent increasing or not. And once this the increase is larger than a certain threshold, then you are going to stop and claim that the change has happened. So this Q-sum is also related to SPRT. I'm sure if you take estimation and detection, you know this as SPRT. What we can do is that at each time we start a new SPRT. Okay, so we are going to start SPRT at time 1, and then start another SPRT at time 2, start another SPRT at time 3. As long as one of them cross the upper threshold, then we are going to stop. Okay. So the Q-sum is the one in which one of them, as long as one of the SPRT exit this area from from the upper boundary. Okay. So it's the TP is the first SPRT that goes up at this threshold speed. Okay. So this will be useful in analysis in the later. So this is the case in which we try to minimize the worst case detection delay. But in certain applications, this delay measure is very strict. It's too strict. So there's another problem formulation. It's called Planck formulation. So the main difference is that in the previous case, we tried to do the worst case detection delay, right? So now in the Planck problem formulation, we are going to replace this essential soup with average. Okay? So it's only one worst case. It's not worst case. It's the average worst case. It's the average. So the idea is to replace this essential soup with this average, and the false alarm constraint is the same. So again, our goal is to minimize this quantity subject to this false alarm constraint. And but unfortunately, once we modify this essential soup to average, then we don't know the optimal solution. The problem is too difficult. But we know that the Q-sum, the scheme I just described, although it's not optimal, but is asymptotically optimal in the sense that if this false alarm, if this quantity goes to infinity, then this Q-sum, the scheme I just described, is asymptotically optimal. Okay. So these are the standard results. Okay, these until now I'll just give you some high-level idea about what has been done for the change point detection. So now what our work is on this kind of energy efficient quickest detection. So the main idea is that we are going to take the energy required for sample into consideration. Okay? Because normally these kind of schemes, they are used for the sensor network. Okay? For the sensors, they are put into the bridge, or sensor put into those near volcano to monitor whether there's some structural change. Okay? So for those sensors, we have to consider the energy constraint. Okay? So there are some papers by Professor Valvelli at UC. They consider this kind of change point detection with energy constraint. What they do is that they put additional term in the cost function. Okay? So remember, this is a cost function for measured delay, and then they put additional one which measures how much energy you use for your scheme. So so what they try to do is minimize the linear combination of these two terms and with this same false alarm constraint. But we think that their scheme is kind of, you can think of their scheme is kind of a soft energy constraint. What does that mean? This means that, of course, they want to minimize the energy they used for taking samples, but they can go ahead and take samples at any time as they want. Okay? So what we have done is that we consider two different problems. The first one is the quickest detection with total energy constraint. You can think of this as a sensor which is powered by battery, okay? Because the energy you have in the battery is limited, which means that the total number of samples you can take for this kind of change point detection is also limited. Okay? So now the question is that even if you only have a limited number of samples you can take, so which means that you have to skip some of the samples. Okay? You cannot observe all the samples all the time. You have to skip some of them. In this case, how are you going to use your energy most efficiently, and what is the best way to detect this change? And then our second line of work is about this change point detection with stochastic energy arriving constraint, which along a similar line as Professor Yes is working on, but we are looking at the problem from a signal processing perspective. So what we are trying to do is that we assume that the sensor is powered by energy coming from the renewable source. Now the question is that if we have this kind of constraint, then we cannot take samples at any time, right? So you can only take samples if you have energy in your battery. And now if you have energy in your battery, how are you going to use this sample rise to minimize the detection delay? Because in our case, if you take samples before the change, you are wasting your energy, right? Because what we care is this change. Okay? So what we care is about what happens after the change. But if you do not take samples, then you don't know what's going on, right? Then you're not quite sure whether change has happened or not. So there's a trade-off there. On one hand, you don't want to waste too much energy before the change happens. But if you do not go and take samples, then you don't know, you don't have any information about the environment. Then it's difficult for you to make decisions about whether the change has happened or not. So yeah, this is one of the applications. So suppose you put sensors on the bridge, and the sensors is powered by renewable energy coming from the wind or solar or even the vibration of the bridge. And we want to use these sensors to monitor the health of the bridge. Then the problem is how are we going to use the energy coming in, and how we are going to design the detection scheme to detect any change in the bridge. So now I'm going to start with a simple model in which we assume that the energy comes on here as a binary random variable. Okay. So later on, I'm going to generalize the case for the general energy arriving model, but just to get some idea what's going on, so we first consider this binary energy arriving model. So again, the problem formulation. So again, we have a sequence of random variables, okay, x1, x, and this sequence of random variable, the PDF will change at a certain time. We don't know, and we want to detect this. Okay. So we have this energy arriving process. So we use AK to denote the time instance in which you have energy come. Okay. It's a random process, and we use mu of k to denote this energy arriving process. If mu of k equal to 0, which means that I don't have energy coming at this particular time. If it's 1, means that at this particular time I have 1 unit of energy coming. And so here, mu of k simply means whether I have energy come or not. Then A of k is the time instance in which the energy comes, right? So A1 simply means A1 equals 1 means that at time instance 1, I have 1 unit of energy. A2 equal to 4 means that at time instance 4, I have energy coming, and A3, A5, and so on and so forth. So we use B of k to denote the observation time, which is the time you are going to use your energy. Okay? So B1 equal to 3 means that I'm going to use the first unit of energy at time 3. Right? B2 equal to 6 means that I'm going to use the second unit of energy at time 6. Right? Of course, I mean, if the energy comes, you can decide whether I'm going to store it in a battery or I'm going to use it. So the time you use it and the time the energy comes, they don't have to be the same. Right? So, but the only constraint is that the time you use the energy has to be later than the time the energy comes. This energy causality constraint. So similarly, I'm going to use mu of k to denote this energy spending decision. Right? So if mu of k is equal to 0, simply means that I'm not going to use any energy at this particular time. And if mu of k is equal to 1, means that I'm going to use this energy at this particular time. So it's very simple. So
the only thing you need to spend energy on is taking the sample. The only thing you use the energy for is to take the sample.
Yes,
because,
we assume that taking a sample. I mean, you can also think of the energy spent by taking sample and computing this. Computing
whether you think you stopped or not.
Yeah.
Okay.
So we assume that the amount of energy you need is same as 1 unit of energy comes. So in this particular setup, we assume that there's a match between the energy come, the unit of energy come, and the unit of energy you use. But this will be relaxed in the later part talk. So now I'm going to use Z of k to denote the observation you take, right? So if mu of k is equal to 1, simply means that if you go ahead and observe the sequence, then you know xk. But if you do not spend any energy, then you are not going to get any observations, right? So you are going to miss a lot of observations. So phi simply means that there's no observation. Then you take a sample, you get one observation. Then you take another sample, then you wait 2 more minutes. Then you take 3 samples in a row. Okay. So we are going to use ZFK to denote the observation, the samples you take, the sequence you observe. So sometimes it will be empty, sometimes it will be the real samples. So there are quite a few probability measures. I'm going to skip here. Anyway, so this PFT simply means that this is a probability measure in which the change happens at time t, right? EFT is average over this. And the P infinity simply means that there's no change on the sequence. So all the samples, they are coming from F naught. And the average is also same, meaning that there's no change. So if you compute this average, then you need to compute over the F naught. Similarly, then we also have a probability measure for the observation sequence, because this observation sequence also depends on how you use your energy. So of course, we have this energy causality constraint. You cannot use your energy before it comes, right? So this is the energy dynamic. Right? So at time k, so this is the energy left, and then this is energy arrived, and this is the energy you use. Okay? So we need to make sure that this E of k is always larger or equal to 0. And then in this kind of binary case, we can simplify this to the case in which the time you are going to use the energy should be later than the time the energy comes. Okay? So this is we can simplify this in the binary case, we can simplify this notation. Then all the energy spending policies, we have to make sure that it satisfies this energy causality constraint. Okay? So this is the set of strategy which is allowed. Okay?
And you also have C is the battery constraint.
Hmm?
C is the battery.
Yes, C is the capacity of the battery. This capacity is limited. So now this is the problem we are trying to solve. Essentially, we are trying to solve the same problem as the classic change point detection problem with this additional constraint. Meaning that we want to design a stopping time in which we are going to raise this alarm, and on top of that, we want to design our energy policy that satisfies this constraint. Okay, that satisfies this causality constraint. So we want to design the scheme in which how you are going to use your energy and how you are going to raise alarm, but we will try to minimize the detection delay with these 2 additional constraints.
Can you give us kind of an intuitive sense of why you wouldn't just, if you have the energy, take the sample?
Yeah.
Why that policy, which is kind of myopic, is bad? Like,
actually, it's good.
Oh.
We are going to show that it's good. But I'm going to show that in the next slides. But that's the scheme we end up. At the very beginning, we thought that because it makes some sense to. Because at the very beginning, we know that the change has not happened, right? So it makes some sense to.
Well, I don't know. I mean, it depends on your model for the change, right?
Yes.
Like, are you using like a Bayes type model for this version of the stochastic energy version of the problem? Is there like a distribution of the change?
So we consider non-Bayesian. In this problem, we consider non-Bayesian problem.
So. How do you
that's true. That's true. But on the other hand, you can also, but you have this Q-sum statistics, right? When you take some samples, then you have this. You have some idea about whether change has happened or not, right? So then you can use that quantity to decide whether you want to save energy for the future or not. Because if this Q-sum is very small, which means that the change has not happened yet. Right? So the other way to say will be okay. If the energy level in the battery is very low, they also want to save some energy. So at the very beginning, we thought that a good scheme should combine both, consider both Q-sum and also the energy level of the battery. But we end up, as you mentioned, so I'm going to say that the scheme you mentioned actually is very good. But it's not optimal. We cannot show that it's optimal because of this problems, but we can show that it's asymptotically optimal. So the problem is very difficult because the observations, they are not conditional IRD anymore. Because we have this, because of this energy process, you introduce some correlation into the observations we take. And also we have this two coupled decision rules. One is detection rule, the other one is this energy usage rule.
If the energy model is like IID, energy arrival?
In this case, it's IID. But the conclusion we can also generalize to the Markov case, Markov alloy model, because the proof can be extended to that. But in the talk, I'm going to only consider IID case.
So what's the difference between capital M and capital T?
Okay, so this capital N is number of samples you take, average and the number of real samples you take, and this T is the total time. Because so that when you take samples, the time interval will change, right? So N is the number of samples you take, then T is the total time you spend.
So that seems to be one of the main differences, right, in your structure.
Yes, I mean we consider three different problems. So in the first problem, we only constrain on the number of samples you take if there's no false alarm.
Can you explain the intuition between these two constraints?
Oh yeah. So okay. So in this particular problem, we want to minimize detection delay. Okay. Subject constraint that if there's no change, I want to make sure that the number of samples you spend should be larger or equal to a certain threshold. And now in this problem formulation, you want to make sure that the time when you raise the first alarm should be larger or equal to a certain value. So the main difference is that this problem formulation will be useful for the case in which you are not quite sure about, there's uncertainty about the energy allowing model. Because when you take this, when you compute this one, it doesn't depend on the energy allowing model, right? It simply is the number of samples you take. And in this particular case, if you want to compute this quantity, it really depends on the energy allowing model. So this will be more useful for the case in which there's no energy, you are not quite sure about energy allowing model. So it will be more robust. They are related, but this one is easier to solve. So yeah, so the main conclusion of our scheme is that a greedy scheme in which, as long as you are going to spend energy as soon as it comes, then at the same time you are going to use Q-zone, okay, use the same old rule. Where it is actually optimal for the first problem formulation, and is asymptotically optimal for the second and the third problem formulation as this average run length to false alarm constraint close to infinity. So as you can see that this scheme is very simple because for Q-zone, Q-zone is very simple. The complexity is very low, and also this this strategy is also very simple. So it's very useful for the sensors with very limited energy, and it turned out to be a very good scheme. So I'm going to give some high-level ideas why we have these kind of results. So the first result that is very important for this non-Bayes case is something called Equilateral. What this means is that in order for a scheme, remember in the non-Bayes case, what we are going to do is the cost function is the worst case detection delay, right? So now what worst case over time t. So what this equilateral rule simply means is that the detection delay of your scheme is the same. Doesn't matter when this change time happens. Because our cost function is the worst case scenario. So if your scheme is good, it has to be good for all the scenarios in which the change happens. So if you design a scheme in which is good for a particular value of t, but it's bad for some other value of t, then because the performance measure is the worst case. So it doesn't matter whether it's good for some certain value, the penalty will be the worst case scenario. So your scheme has to be good for all the change time. And this is what's happening. So we show that our scheme, this kind of greedy plus Q-sum actually is this kind of equilateral, which gives some indication that this might be a good rule to follow. And indeed, this is the main reasons why that this kind of simple rule is good for the problem we consider. And then another implication is that since the detection delay is the same, doesn't matter what is the change time t. Now we can simply focus on D1. Means that we can go ahead and assume that change happens at time 1. Now the problem then is a sequential detection problem. It's not change point detection anymore. Because when we try to measure D1 simply means that the change happens at very first, right? Then all the samples they are coming from F1. Then when we analyze the scheme, we can the analysis is similar. Then go back to SPRT. So now, in order to show that our scheme is optimal for the first problem formulation, then there are two steps. The first step is that we show that for any power allocation, Q-sum is optimal. And then after that, we show that under Q-sum, this kind of greedy is optimal. Then in the proof, we use some relationship, the relationship between Q-sum and SPRT, and I'm going to skip the details. But the main idea is the relationship between Q-sum and SPRT. Now, next I'm going to talk about asymptotic optimality for P2 and P3. And this will depend on the paper, this paper. And this is the first paper I published.
This is you, 1998?
Yeah, this is me. No, this is not. I gave this talk at Syracuse and told them that this is my first paper, but Syracuse in me knows me very well, right? And she said, at that time you just entered college, how can you publish a paper? Then I thought that this is my brother and we read it, but actually it's not. And this is a professor at Stanford. And this is a very famous mathematician there.
Right.
Yeah, so this is his paper. So and turned out that we have the same last name, which is always good, because his paper gets cited a lot. And in our area, I'm the only one who has this last name, right? Then if they didn't know, they say, oh, this is Lifeng's paper, so it's good for me. But anyway, so the main idea of this paper is that so remember the main problem for the main technical issue for the problem we are working on is because of this correlation introduced between the samples. And this is one of the papers that have us. There are some tools you can use to handle this issue. The main idea is that this result shows that as long as you can bound how much information you can get from the samples you take, then you can bound the detection delay. And this is how we can use this result. So remember, for the Q-sum, at any time we are going to, what we do is that take a look and see how much increase we have, right? So this paper shows that as long as you can bound how much information each sample can tell you, then you can lower bound the number of samples you have to take.
So I guess that's something I was asking before. If the change never happens,
yeah,
does this just keep monotonically decreasing?
No.
So it does bottom out to some minimum.
If
Q-sum itself.
Okay, so the decrease is not monotonic. Sometimes it will increase, sometimes it will decrease.
Right, but
so if change never happens, then if this decrease just happens that you have a sequence of an increase, then you are going to raise a false alarm. So we want to minimize the event, this kind of event.
Right.
So if the change never happens, then over the long run it's always decreasing. But on average it's going to decreasing. But each time what you get is random variable. So it could be the case that it will increase use for a certain time.
Okay.
It's a random walk. What we really need to do is to bound how much information each sample will give you. Okay. So how much information each sample we are able to give is going to give you. So this is what we did. So what we do is that for any power allocation scheme, doesn't matter what you do, we can bound how much information you can get from all the samples over a certain time of period, and then we can use the technique from that particular paper, and we can show that there's a lower bound. So it doesn't matter how good you are, doesn't matter what kind of detection scheme, what kind of power allocation scheme you use. The detection delay has to be larger or equal to this number. Then what we can do is that we show that this greedy prosecution achieves this lower bound, which means that this lower bound and upper bound match. And we can show that our scheme is asymptotically optimal in the first order asymptotically optimal. Similar for the third problem formulation. Remember, in the third problem formulation, we want to minimize the average worst case scenario, average worst case detection delay. Okay. So again, what we can do is that we use the relationship between QSUM and SPRT. Then once we go back to SPRT, then the problem will be easier. Then we were able to compute this lower bound, upper bound, and we show that they match. Okay. So after doing this kind of boundary model, we have a good idea about what's going on, what kind of step we should use. Then we generalize to the case in which of this energy, we have this more general energy arriving model. So in this case, the energy comes not only random on time, it's also random in amount. Okay, so at a certain time there's only one unit of energy, or 0 or 2 or 5. So it's it's random in time, also random in amount. Okay, so we use this again. We use this to denote how much energy comes. If it's equal to 0, which means that at this particular time, there's no energy come. But if it's equal to 5, then it means that at this particular time, I have 5 units of energy. And again, this is how the energy process at your battery will evolve. This is the energy left after the previous time slot. This new energy comes, and this is the energy you use. Again, we have this energy constraint, this energy quadratic constraint. So EK is larger or equal to EK is always larger or equal to 0. So in this case, we found out that this generalized greedy scheme is very good. Which means that this simply means that if you have energy left in the battery, you should use it. Okay. If you have no energy in the battery, you have no choice but to stop. But do not take any sample. Okay. So this is a greedy energy allocation scheme. Plus this QSUM again is also is good for this kind of more general energy arriving model. And we also so again in this here we still assume that the energy comes RD, but in fact our proof technique can be generalized to the case in which this is a Markov process. The energy arriving is a Markov process. We can the result. This conclusion still holds.
I find it hard to believe it would hold for the Markov process.
So what? Okay.
Suppose you had a process that, like it's an on-off energy process. Like you get sunlight for 12 hours, and then you have 12 hours of darkness.
Of course, right? It's not over this such scale.
Well, but I'm making those just to relate them to kind of the reality. You know, it has really to do with the question of how big your battery is, and if you have an on-off process, it seems to me that during the on period you have to save some energy for the off period. Like you could throw away the battery constraint, just be like.
So if you throw away battery constraint, then actually what you said is actually very true. But for the problem, you consider the battery is finite, right?
But even if you have a finite but a big battery, right?
That's
like
true.
a battery big enough to save enough energy for the nighttime when.
But what really happens is that so anyway, so the battery size doesn't matter how big it is finite, right? Then what we say is asymptotically optimal simply means that the detection this ARL goes to infinity. Okay, so it doesn't matter how much energy you have at battery. You can only take finite number of samples. This finite number of samples will give you, even if you go ahead and save this energy for the future use, this finite number of samples, the amount of information they will give you will be limited compared with the time, the false alarm constraint. So this is finite, and this goes to infinity. Then it doesn't matter how smart you are, the energy you save, if you divide the time, will be minimized. So the key here will be the finite value of this battery.
So in that context of there's night and there's day, maybe you'll be late by a day. Is that fair?
That's true. That's true.
But asymptotically, that's okay.
That's okay. Because if you think about it. So if you this is for example, if you monitor for the bridge, right? You want to make sure that the false alarm. So what I mean by infinity means that the time between false alarm. Right? So the time between false alarm in the bridge contact, you should want to make it years, right?
Well, it depends. If the bridge is going to be, dangerous, you want.
But if you want this bridge, it's a very busy bridge, then it's a false alarm, then you're going to close it, and then the cost will be very high.
Not as high as the bridge collapses, the cars go in the river, right?
That's true. That's true.
It's not.
But normally, I would assume that you want to make sure that the false alarm is in the unit of years instead of unit of days, right? Because if the false alarm is unit of days, then you have to close it every week. The cost is too high, right?
Yeah.
So it's okay to close it in every 2 or 3 years, but if you close it every week, that's not good. Not good way to maintain a bridge.
That's, we're kind of, I gave you a model with sunlight and nighttime, and then you went to the bridge. I mean, presumably, if I were faced with your situation, I would have a second test for the bridge that's a better test that doesn't involve closing it, right? So if you have a test that involves driving a truck out there and guys setting up some very fancy measurement equipment, maybe they could do that every month or two.
That could be true,
right?
Yeah, but
so really,
that's true. That's true. But we assume that if that problem, you have to close it. So as a safety measure, right? So, but anyway, so the key here, what we were able to show this actually is in fact is really depend on the size of the battery. So if you can allow this the size of the battery goes to infinity, then the scheme is not asymptotically optimal. So our proof really depends on the assumption that the C is finite. Then we let this false alarm goes, the average runners between false alarm goes to infinity, and that's how we can get those kind of drops. But I guess in the case in which if the C, the battery size also increase with this false alarm, then the situation will be different. But that's not. We have thought. I give this talk in a workshop, and someone pointed this out to me, and we were trying to see what's going on there, but we haven't got any good result on that point yet. So yeah, I think I'm running out of time, but I'm going to skip here. So the steps are similar. So what we do is that so we provide lower bound, upper bound, and then we show that this lower bound, upper bound match, and then we are happy. Since they match, then we are happy. And so yeah, I'm going to give you some simulation figures to see what's the impact of this energy allowing process on the detection delay. So in this curve, this line, this dotted line, and so this direction is the detection delay. The detection delay. This is a false alarm rate, and as you can see that for different value of probability, this red line, this is for the boundary energy alarming model. So if p is equal to 0.8, then the delay is quite close to the case in which you can take samples all the time. But because the energy comes very slowly, if it's only 0.2, then it's quite far away from the case in which you can take samples all the time. And all the other figures, they are also showing the similar case. So let me offer some concluding some remarks. So we consider this change point detection problems with this stochastic energy arriving constraints, and we found out that this greedy strategy, greedy power allocation plus Q-sum is although it's very simple, but it's a good rule, good in certain sense. And we also generalize the case in which generalize the model to the we consider this a binary model. We also consider this more general energy arriving model. And we show that this greedy and plus Q-sum is also good for both cases. And this is my talk. Thank you.